At the foundation of modern computing, hardware diverges into two distinct branches. One is designed to process massive streams of data at blistering speeds. The other is engineered to exert precise, real-time control over the physical world. The first branch is the microprocessor, or MPU. This is an isolated, high-performance computation engine. It cannot function on its own. It requires an elaborate external infrastructure, a motherboard, to provide it with memory, storage, and interfaces. The second branch is the microcontroller, or MCU. This is a highly integrated system on chip. It takes that processing core and combines it with memory and hardware interfaces directly onto a single, self-contained silicon die. Selecting between an MPU and an MCU forces a strict engineering trade-off. You are choosing either raw data throughput or deterministic low-power hardware control. We can see how this trade-off works by mapping the architecture. This block diagram illustrates the microprocessor core. Inside, it houses the arithmetic logic unit, the control unit, and high-speed cache registers, but it connects to nothing directly. Instead, it relies on complex external address and data bus lines. An MPU contains no internal RAM or ROM. It must fetch every instruction and store every variable using these external memory modules. It also cannot talk directly to hardware. It manages peripherals through an external I/O controller, adding another layer of physical separation between the processor and the outside world. This modular architecture serves a specific purpose. By offloading memory and peripherals, the MPU dedicates all its internal silicon to computation, achieving clock speeds in the multi-gigahertz range, at the cost of high power consumption. Because the memory is separated and the processing speeds are so high, an MPU requires a complex operating system to manage resources and run multiple applications simultaneously. This is the exact architecture operating inside an Intel Core, an AMD Ryzen, or an ARM Cortex-A series chip. MPUs deliberately sacrifice physical footprint and power efficiency to maximize raw processing capability. The microcontroller reverses this priority. It compresses the external motherboard components into a microscopic space. The CPU shrinks, and the RAM and ROM are pulled directly inside the perimeter of a single silicon die, creating a system on chip. Because the goal is physical control, the MCU integrates dedicated hardware peripherals. General Purpose Input-Output, or GPIO, allows the chip to manipulate external pins directly using digital high and low signals. To read analog sensors like temperature probes, the MCU uses internal analog-to-digital converters. Digital-to-analog converters handle the reverse, bridging the physical and digital domains. Hardware timers and pulse width modulation modules are also baked into the silicon. These allow for precise motor control and timing operations without demanding constant attention from the central CPU. This integrated architecture defines the legacy 8051, Microchip's PIC and AVR, the STM32, the ESP32, and the ubiquitous ARM Cortex-M series. The MCU is structured to interface directly with physical hardware in real time, functioning as a complete system rather than an isolated calculator. Because an MCU operates with strictly limited internal memory, that space must be organized efficiently. This segmented map separates flash memory, which stores the permanent application code, from the volatile RAM, used for operational data. Within the RAM, the stack manages local variables and function calls in a strict sequential order. The heap handles dynamic memory allocation, organizing data on the fly as the program runs. For critical calibration parameters or settings that must survive a complete power loss, MCUs utilize a dedicated section of EEPROM memory. To interact with external modules like sensors or displays, the MCU core relies on hardware-level communication protocols that require minimal processing overhead. UART provides simple, two-wire asynchronous communication for basic device pairing. For higher speeds, SPI uses a master clock line to synchronously transfer data packets to multiple peripheral nodes. I2C allows for complex networking of multiple devices across just two wires. In industrial and automotive environments, the CAN bus provides robust, error-resistant communication through differential signaling. These embedded protocols are lightweight and highly deterministic, contrasting sharply with the massive software overhead required by MPU standards like USB, Ethernet, or Wi-Fi. MCU memory and communication are strictly engineered to ensure low latency, predictable data flow, prioritizing immediate action over bulk storage. Programming a self-contained MCU requires bypassing an operating system entirely. Developers write bare metal code using languages like assembly or embedded C and C++ to manipulate specific hardware memory registers directly. This process starts in an integrated development environment. Engineers rely on industry-standard platforms like STM32Cube IDE, Keil U-Vision, MPLAB-X, or Platform I/O. The human-readable C code is passed through a compiler and a linker. These tools translate and optimize the logic into a final, machine-readable hex or binary file. During the flashing step, debugging hardware pushes this binary file across a USB or JTAG interface, permanently burning the instructions into the MCU's internal flash memory. Once powered, the execution phase begins. Instead of launching independent user applications like a desktop computer, an MCU typically runs a single infinite loop or utilizes a lightweight real-time operating system to manage its tasks. The entire embedded software lifecycle is focused on one objective: bridging low-level software instructions directly to physical hardware states. Comparing the two architectures reveals distinct operational profiles. The MPU is an expensive, thermally demanding component. The MCU is ultra-cheap and battery-efficient. An MPU's operating system introduces unpredictable latency, making it unsuitable for exact timing. The MCU guarantees deterministic, microsecond accurate responses. The MPU dominates in processing speed. The MCU dominates in integration and determinism. MPUs are deployed in systems requiring heavy OS overhead, bulk data processing, and complex graphical rendering: laptops, smartphones, aerospace navigation systems, and AI edge servers. MCUs are deployed for localized, single-purpose tasks. You will find them controlling the spin cycles in washing machines, managing timers in microwaves, and driving smart agriculture irrigation networks. In safety-critical applications, MCUs are non-negotiable. They are the primary logic units inside industrial PLCs, robotics actuators, drone flight controllers, and the electric control units of electric vehicles. Hardware selection comes down to a single question: is your system's primary constraint processing vast amounts of data, or safely actuating physical hardware? Historically, the boundary between these chips was absolute. Today, it is blurring. The rise of TinyML allows highly optimized machine learning models to run directly on low-power Cortex-M microcontrollers. This convergence is driving an expansion of MCU deployment across modern infrastructure, acting as the foundation for Industry 4.0, industrial IoT networks, and smart city automation. Mastering these architectures opens specific engineering career paths, ranging from embedded systems and firmware engineers to industrial automation developers. To build a career in these sectors, deviautomationsolutions provides the training and technical infrastructure to master these embedded ecosystems. They deliver comprehensive solutions across industrial automation, PLC programming, HMI and SCADA systems, artificial intelligence, robotics, and dedicated technical training. Subscribe to Devia Automation Solutions for more educational content, and contact deviautomationsolutions@gmail.com for professional business inquiries.